So introduction also, already it has been given a lump. So let us take up the slope deflection method. So slope deflection method, as the name itself indicates, it is a method of analysis of structures, indeterminate structures, using the displacements at the ends of members. So you already know, if you take any member in a prismatic, any prismatic member in either a beam, frame or truss, whatever it is, subjected to some kind of loading with some boundary conditions at the ends, some end conditions at the ends, undergo two types of displacements. One is translatory type of displacement, another is rotation. Translatory type of displacements will use of two types. One is horizontal, another is vertical. Next, another is rotation about an axis normal to the plane. These are the only possible displacement at any end or any point of a plane frame structural member. You take any plane frame structural member, plane, all the members play in one plane, plane frame structure, it is a one-dimensional structure. If you take any plane frame structural member, the possible displacement at the ends are two translations and one rotation. In slope deflection method, we assume the member to be axially rigid. So that means this particular displacement will not be there at all because member is assumed to be axially rigid, so it will not undergo any elongation or contraction. Rigid means it doesn't undergo any sort of deformation axially. So this horizontal displacement will not be there. You will get only vertical displacement and rotation. So these are the only possible displacements at ends of any frame structural member. Now here this rotation we call it as the slope, this translation we call it as the deflection. So in terms of this slope and deflection at the ends of the member, the force developed at the ends of the member, we are going to develop a relationship between that force developed at the ends of the member in terms of these displacements. That means if you call this displacement as theta A and this displacement as theta B, this YA, YB, the relative displacement between AB in the vertical direction, that relative displacement is nothing but difference between the vertical displacements at the two ends, that is YB minus YA, that is the relative displacement of in the vertical direction between the ends of the member, that we call it as the sway in the member. So that sway delta is YB minus YA. So we develop an equation in terms of these displacement for an equation which represents the moment at the end, any end of the member in terms of these displacement. That is, we can develop that relationship as MAB, the force developed or moment developed at the left end is given by 2EA by L into 2 theta A plus theta B minus 3 delta by L plus or minus MAB bar. This equation, how to develop, we will take up a little bit later. This we call it as slope deflection equation because these are the slope, this is relative deflection, and the force developed in terms of this slope and deflection, we call it as slope deflection equation. So this is the force developed at one end, and similarly force developed at the other end, that is MBA, is again same thing, 2EI by N. This will be theta A, this will be 2 theta B, this term remains same, and this will be MBA bar. This MAB bar, MBA bar are nothing but the fixed end moments developed at the ends of the member. Fixed end moments means the ends are assumed to be fixed. The ends, if you assume them to be fixed, there won't be any displacement allowed because they are fixed. Because of these ends, wherein there is no displacement at all due to the load, whatever the end moments which are going to develop, that we call it as MAB bar and MBA bar. So, the net moment developed at any end of the member will be the moment developed due to no displacement occurring, and moment developed due to this rotation theta A, rotation theta B, and translation delta. This we call it as slope deflection equation. Using this for any member, there will be two equations. One represents left hand moment, another represents right hand moment. Any member, if you take, you will have two equations. This equation you have to write for all the members given in a structure for analysis purpose. Then, when once you write all the equations, then you put the values of this displacement, because in the given structure, these displacements may be possible or may not be possible. As I told you here, fixed end moment, if you have fixed end or fixed joint, there won't be any displacement at all. Since A is fixed, theta A you may have to put 0 like that. So depending upon the end conditions, so you have to put the appropriate values whether it is going to occur or not during the loading. Then you have to again rewrite the equation and then apply equilibrium condition at each joint. You will get a set of simultaneous equations. Those equations you have to solve for these displacements which are bound to occur. When once you solve, again come back to this slope deflection equation for each member, because after solving those displacements, you can substitute here, you will get the moment. That's all the analysis. Analysis means you have to find out the forces developed at the ends of members due to given loading. That we are determining by establishing a relationship between the forces developed and the displacement occurring and evaluating those displacements. That's the basic methodology which we are using in this slope deflection method for the analysis of structure. So let us take up a small example and see how we can use it. So in the nutshell, so we have to know the slope deflection equation, which is essentially an equation which relates the moments developed at the ends of the member with the unknown displacements. So the general displacement at the ends of any member are rotation and translations. Another translation, there will be two translations virtually. One translation, that is axial translation, we are neglecting. That's the assumption we are making. We assume all members to be axially rigid. So in the nutshell, we have only two translations. These two translations, we take the relative value. So the general two translations, here it is YA, YB. The one, you keep it as the reference point. The relative displacement, that is the difference between these two displacements, we call it as the relative displacement, YB minus YA. That we call it as the sway. And the sign conventions also have told with respect to displacement, clockwise positive, clockwise rotations, translation, if it results in anti-clockwise rotation, you take it positive, otherwise negative. Like that. You can have those sign conventions and solve the problem. So, I'm wondering.